So welcome to the night shift at JFocus. I'm shocked. People want more learning, even after a full day of conference. And then there are the others that can drop in. Welcome to JFocus and this J4 meeting. Are you awake?
I think everyone's had too much beer. So my name is Vincent Mayers. I live in the US. I'm not from the US. It's a long story. I run the Java user group in Atlanta, Georgia. So I'm very happy to be here with Java Forum and at JFocus and to help to introduce Nikolai over here.
So and we'll have Nikolai here, and we have Alexander as the second talk after this, and then you're welcome up to the JFocus party. By that time we'll have moved to the bar at the end of the building. But I guess you'll find your way. So please welcome Nikolai, and take it away.
Sure, thank you. And there we go. Okay, so you made it sound as if the people have to sit through this to be eligible to go to the party. That sounded like, okay. So, Java makes new versions every 6 months. Thank you for being here. Go to the, no, seriously. Right, so I'm Nikolai Parlok. I'm a Java developer advocate for Oracle, and I'm here to talk about Java Next, specifically the 6 big projects that I have on the slides here. I have prepared way too much, so I might be talking a little bit too fast. I'm sorry about that, but there's so much going on, and all of that is exciting and important that I didn't want to spare you too many of the details. So we're going to go through all of this. If you want to see the slides later, you can go to slides.nipafx.dev/java-next. I'll leave that up for a second. And then we're going to go through all of those. Quick thing, what are projects? Why are we talking about projects? OpenJDK is the community that develops JDK, which is the reference implementation of the Java specification. And OpenJDK is the driver behind changes. So it will observe some thing that is not ideal in Java. It will create a project around that, and that project will take years or sometimes even decades to complete. People will be working, will be researching, will be making proposals, preview features, eventually finalize those, and then eventually they're going to be usable by all of us. These are 6 of the currently ongoing projects, definitely the most important ones, and also that's like 80–90% of the mind space of what's going on in these projects at the moment. So there are a few more, but these are really the important ones. Okay, so let's just get started. We're going to start with Project Panama, which is about interconnecting JVM and native code. Everything that's green on these kind of slides, if it's not code, it's probably a link. So I'll link to the project, to the mailing lists. So if you're interested in any of these projects, you can follow up, you can try these things out, you can give feedback. The links are always there, and there will be more links throughout the presentation on each topic. Okay, so Project Panama can be divided into 3 sub-projects, the vector API and then the foreign memory API and foreign function API. Let's go with the vector API. So if you write a loop like this, which is fairly straightforward, we're iterating over 2 arrays, and we're computing a kind of like a little formula here that says C should be the negative of the sum of the squares of A and B. We're going to go through that array and do that computation. Then that looks straightforward and is kind of nice, but this would be potentially inefficient. Because modern CPUs do something that's called vectorization. They have something that's called vectorization. They have multi-word registers, which allow the CPUs to do a bunch of computations at once. So instead of doing, for example, 1 addition of 2 floats, they can do 16 additions of 16 pairs of floats in basically the same amount of time. So that means a 16x improvement. So that's clearly something that Java wouldn't leave on the table. And so the just-in-time compiler is trying to notice when these loops can be mapped into these specific CPU commands, and it will try at runtime to optimize that. And that works in general, but it's definitely not reliable, because it can only do this if it can prove that the transformation definitely works, right? It's more important that your code is correct than that it's fast. So that means that it has to be proven that this transformation into these commands is doable. And since these vector commands are very different from the way you would regularly write commands, this is not always obvious. So that's why it's not reliable. That's why the vector API was created, which is a little bit more cumbersome, a little bit more indirect, but which allows you to express your computation in a way that can then be reliably optimized. So here what I'm doing here is I'm again having the same float arrays. We're not going to go over all the details. The important part is here I'm running through that array, but I'm not going in steps of ones. I'm going in steps of this vector species length. So for example, 16, I'm going like in steps of 16. I'm going to pull out a float vector, so 16 maybe again, or maybe it's just 8, depends on the CPU. I'm going to pull out more 16 more on here. I'm going to do the math in all of our big decimal favorite way to do math, which is function calls, or method calls, I should say. And in the end, we write it into the resulting array. I'm not here to teach you the details of this API, although it is kind of interesting how to switch your thinking around in this kind of stuff. So for example, this API doesn't really allow branching. If you want to do something with an if, you have to do clever tricks. And we're not going to talk about that. But this API is really interesting to use, and it is comparatively clear and concise given the requirements, which are that this should be reliably compilable down to these vector instructions across different CPUs, right? AMD, Intel, shouldn't matter. Should be possible to compile this down to that. And if you run a CPU that doesn't support this, it should degrade in a way that it will not be slower than the loop would have been. So that's the vector API that is currently being worked on. I will get to what the exact state is towards the end of each section. I'm going to give you a little bit of a timeline of where things are standing. Before getting there, I want to talk about the two other projects that Panama is working on, although that blend together pretty seamlessly. Let's talk about foreign memory. Foreign memory means storing data off heap. Somewhere where it's not the garbage collector who's in charge of the memory, but where you think you're doing better than the garbage collector for whatever reason, or maybe you just want to keep the garbage collector away because you want to call native code, so it doesn't rearrange the data while some C code is running somewhere. So you want to store stuff off heap, and that is tough. Originally, you only had the byte buffer, which is somewhat inefficient and limited to 2 gigabytes, and also doesn't really have a very nice API. And then there's unsafe, which does not have this limitation, is blazingly fast, but is unsafe. It is a big foot gun, and it's not really supported. This unsafe could theoretically disappear from one Java release to the next. It could be different on Oracle JDK versus some other vendors JDK. This usually isn't the case, but technically it could be because it's not part of the standard. So that's why using unsafe is definitely not recommended. So instead, a safer and more performant foreign memory API was created. I'm not going to show it here because, first of all, it doesn't even fit on a slide. Like working with that is a little bit more, takes a little bit more code. Because it goes into a little bit more detail, it gives you types like arena, memory segment, segment allocator, memory layout, var handle. It gives you these types because you're modeling a non-trivial problem, and so it should it has a non-trivial API to let you work into the level of detail that you need to work on. One thing, for example, this API does much better than byte buffer is you have control over deallocation. If you reserve 10 gigabytes of memory, you have a vested interest in these 10 gigabytes to be freed up immediately when you stop using them. Whereas with the byte buffer, this would happen at some point in the future when the byte buffer instance gets collected by the garbage collector. And that could happen potentially really late in your runtime. So that's all I'm going to show you about the foreign memory API. Let's talk about foreign functions. So foreign memory is memory not in control of the JVM. Foreign functions or foreign code is code that is not run on a JVM, predominantly C code. JNI, the Java native interface, does allow you to interact with that, but it's not great. People have used it. Who has used JNI? Who enjoyed using JNI? Wait, but didn't you raise your hand on the first try, did you? Okay, good. So, okay, so it's 1 out of, okay. So not many people enjoy working with JNI. Not everything is going to be super easy in the future, but the foreign function API will make things easier. The idea here is that you use var handles to interact with, var and method handles to interact with the native code, but you're not going to write that code yourself. You're going to have JExtract, which is a tool that will create those method handles from a header file. So you point at a C file, for example, and it will generate a Java file that contains all the nitty-gritty details on how to call into that C code. And that will probably be an API that is not very enjoyable to use from a Java perspective. So the idea is that you will then write a Java wrapper for this Java class, which is already meaning you're writing Java code against other Java code. And if then the native library changes, we rerun JExtract, you get a new file in the middle, and then the Java compiler will tell you if the API changed in a way that is now no longer compatible, the types don't line up, the method names were changed. So this makes these things easier, has been really well received. So overall, the community has started using it. And this allows, for example, easy development of libraries that rep C. That could be a gaming engine, that could be something related to machine learning, that could just be operating system calls. So there's lots of stuff there that in the past you could already do with JNI, but now hopefully become sufficiently easier that it's more likely that people will actually do that. Okay, so Panama is about connecting Java with the native world and offers safer and performant, but also more detailed APIs to mirror the complexity of the situation that you're in. And now let's talk about the timeline. So in JDK 21, in case you're on that, you will not be able to use any of these. Well, you can use both of these APIs, but they are still in preview and incubation, which means they might change. JDK 22 is the one that finalized the foreign function and memory API. So if you're into dealing with C code from Java, then JDK 22 is the release for you to be on, or later, of course. At this point, you shouldn't be on 22 anymore. You should be on 23, going to 24 in March. And then in 24, Vector API is still in its incubation, so it's like the 9th incubation. The first couple of incubations really changed the API a lot, but it has been very stable for a while. The main reason why it's not finalized is that it's waiting for Valhalla's value types. For implementation details, you can ask me about later if you're interested. But that means that it will probably stay in incubation for a while longer. And once it's out of incubation, its API might change a bit, but probably not much. So if this is like mission critical, if being able to use vector instruction on the CPU is mission critical to you, and you would be willing to rewrite a bunch of code in a year or two, or whatever, however long it takes for this to finalize, then you could use the vector API. Incubation or preview does not mean this is a garbage feature that is like an early alpha. It just means it is as good as the features are that OpenJDK usually ships, but it might still change. There might still be a minor change or maybe even a bigger change, and theoretically could even be removed, which did happen in the past once. So it's less, you know, it's not as backwards compatible, you would say, as the rest of Java, right? You cannot bet the house on it, unlike with the other Java features. If you want to dive, all right, so the current work, what's currently being worked on? What is being worked on in Panama this year? And when I say what the current work is, I want to really state very clearly that does not mean that somewhere during this year we're going to see the fruits of that labor, right? That doesn't mean that the next JDK release is going to contain what is currently being worked on, because nobody knows that. Maybe the people who do the work know, but you know, I don't ask them because they don't want to tell me, because then I'll tell you, you know, and they don't want to make these public announcements. So I'm just listing in this section what is being worked on, and then we hope to see those things soon. So memory access performance of the foreign memory API can still be improved. Because I mentioned that they use method handles, this has a certain startup and warm-up cost that can be improved in the future, hopefully. There's a concept of record mappers, which is really cool. The idea here is that you use Java types like interfaces or records, and then you have an infrastructure like a mapper that really knows how to map that to a struct, so that you can just write a Java record, and you know, so that on the other side of the API, you just use it as a C struct, for example. And JExtract gets improvements internally, refactorings, but also the kind of code it generates is improving. Lots going on there. And if you do work with any of this, please do that, try this out, and give feedback on the mailing list. If you want to go deeper into any of this, the Vector API JEP, the current, contains a lot of stuff about that. Then we have 2 good videos on that. And specifically, I want to recommend the last article, which is written by Gunnar Morling. FizzBuzz, he solved the FizzBuzz problem in the SIMD style. So SIMD is single instruction, multiple data. That's what the vectorization is also called, or the concept behind that is called. And that's cool because he runs, you know, FizzBuzz famously has these ifs, right? Like if it's divisible by 3, if it's divisible by 5. And vector instructions don't do it very well, so he has to do some tricks to make this work, and that's really interesting to just dive into the API with this somewhat unsuitable example and see how to make it work. If you want to dive deeper into the foreign APIs, tons of stuff here. The state of the foreign memory support, state of foreign function support, those documents are great. Whenever you see an OpenJDK document that's called state of something, they're usually really well written, so I can only recommend looking into that. Also, we made a bunch of videos on that, and they all seem a little bit dated because not that much changed since then, right? It has been finalized for over a year now, and so that means that, you know, many early videos on that still hold, so you can go and look more at that if you want to. Do you have any questions about Project Panama? You can ask questions now. You can ask questions anytime or at the end. Yes, in the back there. Why is it called Panama? Because it's about, let me see, can I go over for a slide? It's about interconnecting the Pacific and the Atlantic. Sorry, about native code and the JVM. So that's the metaphor here. Like the Panama Canal connects these 2 oceans, Project Panama connects these two parts. And I joked that we should recall to Project Greenland, but that didn't land really well. I think it's too soon to make those kind of jokes. Yes, another one. Yes? So sorry, I can't quite follow. So you're talking about JExtract, and what was the question? Yeah. So what you're saying is that JExtract basically does an incomplete job, like it cannot process all inputs. Yeah. Yeah, but if you already know about the mailing list and you already talked about Maurizio to Maurizio about this, so Maurizio Cimadamoro is project lead on this, then there's nothing I can add to that. So yes, yeah, that is good. I hear your complaint. That's a good point. Yeah, and you're right. Like if you end up writing things manually, then also like it doesn't really work well with C++. I hear because C++ actually is widely unstandardized, so different compilers kind of like have different acceptance criteria. So I hear that I think there's still ways to go. Yeah, definitely. Okay, should we talk about Loom? Let's talk a little bit about Loom. It's about JVM features and APIs to support easy to use and high throughput, lightweight concurrency and new program models. It's quite the mouthful, we'll see what that means. Launched in January 2018, which is impressive because that means it's only like 7 years old and it basically already delivered a big chunk, or the biggest part of the work is already done. Now we're going to see details now. Okay, so let's talk a little bit about through the motivation of Project Loom. Let's say you write an application that has a lot of blocking operations. Maybe it's a web backend that asks a lot the database, a file system, other web servers, a lot of operations that are basically infinitely slow given from the perspective of one JVM, which can do 3.7 billion things a second, but then has to wait for 2 seconds for something to come back from a web backend. So we have two choices. You can use platform threads, which I will use as a term operating system threads. Those are interchangeable from our point of view. So you can use just a regular Java thread that blocks until the task is completed, which is fairly simple to write, easy to debug, but that can limit throughput because you can only use so many operating system threads. They usually have about 1 to 2 megabytes of overhead. And so you can, count out your memories. Thousands of those is okay. Millions of those are probably not okay anymore. And somewhere in between, you lose track of how many you can really have. Usually it's just thousands or maybe tens of thousands, but that's usually where it ends. You can use asynchronous programming, which tries to avoid using a thread while it's waiting, which is great. But some people do enjoy writing that code because it's kind of like the stream pipelines kind of approach where it's like very functional and kind of thing. But I yet have to meet somebody who says, no, it's also great to debug. I love debugging async. That's just my thing. So there's a tension here. Oh, sorry. There we go. There's a tension here between simplicity and throughput. Ideally, you should write simple code that has high throughput. This is where virtual threads come in. A virtual thread is a regular thread that has a very low memory footprint. It's basically just the thread stack, which you always have, right? You can't really work around that. And then just a couple bytes extra, so not a whole lot. A very small switching cost. It is scheduled by the Java runtime itself, which understands your code much better than the operating system would. And the most important part is it waits in memory. So no platform thread is blocked. So while you're blockingly waiting for some operation to complete, it waits. Like mostly, almost all the times. So there are a few exceptions. Pinning means that a virtual thread that is currently being executed encounters some pinning operation, and so far that's neutral, it just keeps going. But then when later an operation happens that blocks, when the virtual thread should then block without an operating system thread underneath, if it is pinned, it will now block the operating system thread too. So that's not good. And that's caused by a bunch of different reasons, by object monitors, native calls, and class initialization, and we're going to go through those quickly. And then there's a concept called capture, which is very similar. Keeping those two apart is not really speaking necessary, but I can't put wrong stuff on a slide or I get yelled at. Capture means that an operation that should block the operating system, should block the virtual thread, but not the platform thread underneath, and now blocks both. It blocks the platform thread, and that is caused by file I/O specifically. So file I/O here is the culprit. So let's go through those. First of all, and the biggest one of this is object monitor pinning. The object monitor is what you're interacting with in a synchronized block when you use wait or notify all, those methods on object, then you're interacting with the object monitor subsystem. And that implementation was bound to operating system threads and just required a lot of work to make it aware of virtual threads. And so the decision was made back in the days, instead of waiting with virtual threads until this last thing is fixed, let's get it out to users early and let's keep working on this. And this is fixed now and shipped with JDK 24, so this is a known limitation back then, but it's now no longer the case. And that means, most importantly, when you do use synchronized, you don't have to worry about pinning anymore. So if you ever tried virtual threads in your code base and you felt that you didn't get the performance boost you were expecting, then that could have been because of if you have lots of blocking operations in synchronized blocks. So now that problem would no longer exist. So you might see an improvement, even if you're using virtual threads, you might see that. But also if you tried in the past and didn't see the improvement you liked, you should try again, because maybe that was the issue and that would then be alleviated. Now we have 2 more cases that are still causing problems. So when there is native code on the platform thread stack, then that's the situation where you still get pinning. So the idea here is you have a virtual thread that calls it to C code, and the C code says, oh, I can operate on the variables that are in the thread stack, for example. In the thread. So it operates on those variables. Then it calls back into Java, so it's already not that common. And then in Java it blocks. Now it's getting really weird. But if that happens, and then the virtual thread blocks, we take away the platform thread, it does other work. Later another platform thread comes along, picks up the virtual thread, and it keeps going, goes back into C, and C says, oh great, that's my platform thread over there. I can just change all the stack variables, but it's now a different platform thread. So now it's running havoc and writing memory somewhere else. So that's not good. So that's why this can't happen. So as soon as you have a native stack frame on the stack, now the threads are pinned, and that means they will not unmount later if they would otherwise. And there is a possible fix in the JVM, but it's really not worth it. Like, it would be a lot of work for a situation that is really rare, because the avoidance here is if you call into native code that calls back into Java code, then try not to block. And even if you do that, pinning is not really a problem. The code will still be correct, but it might not scale that well. So the only time this is an issue when you do all of those things a lot, so that they dominate your blocking situation. So if you do that, unfortunately, virtual threads won't be able to help you. But it's a very rare and unlikely situation. File I/O is a little bit different. So there are limitations within operating systems and the JVM that make it so that if you call into the file system, those operations capture the thread, so the virtual thread does block together with the platform thread. So again, you're blocking an expensive platform thread. There was hope to alleviate that by adopting, at least on Linux, IOU ring, but it turns out that the way IOU ring is written to interact with that from the JVM has a considerable overhead, and that overhead is really sizable compared to how much time you would be spending in the most common case, which is cached SSD reads. Because that's what usually happens. Many reads are cached, and if you care about performance, you're probably reading from SSD. And that specific situation, you don't even get a lot out of it. So it would be a lot of work for not that much benefit, so it's not being done for now. OpenJDK, like any other community that or company or organization that develops software, has to make decisions based on priority. What's the most bang for the buck? Where can OpenJDK improve your development experience or your performance the most? And this was deemed not worth it for now. That doesn't mean forever. And I have seen an open source project that claims to do this right, but I haven't checked it yet. So if you search for virtual threads blocking file I/O, you might probably find it. Okay, so let's talk more a little bit about virtual threads, but is the pinning and capture, is that settled? Are we good on that? Okay, so important to understand is that virtual threads aren't somehow magically faster threads. Each task takes the same amount of time. Arguably, maybe even like a tiny little bit more, because it's actually the platform thread underneath that does the work, and the virtual thread has to be mounted and unmounted, so there's a tiny bit of overhead. But that really is a rounding error. So the latency is basically the same. What virtual threads help you with is latency under specific circumstances. Namely, your workload is not currently CPU bound, and you have a lot of concurrent tasks. If you only have like one concurrent task to the database that takes 5 seconds before it comes back and nothing else is happening in your system, then virtual threads are not going to help you, because you already can do this with one platform thread. You don't need virtual threads for that. And if you're already at 100% CPU, also virtual threads are not going to help you. But most web backends are in neither of those buckets. Most web backends have already a lot of threads running so that they can deal with all the pauses of waiting for the database, for external systems. And those can benefit sometimes considerably in the throughput category. So that's what you're gaining, more throughput. Since virtual threads are so cheap, some behaviors that we trained in the past are not necessary anymore. There's absolutely no reason to pool them. You can just, every time you have a new task that you feel like, oh, I have 2 things to do that potentially block, and I want to do them at the same time, just create 2 new virtual threads. They're basically free. It's like asking how many virtual threads I can have. I heard Alan Bateman, or Ron Pressler maybe, who worked on this, they said once, That's like asking, can I create enough strings to hold all the strings that I need in my application? Which I know you cannot have infinitely many strings. You will run out of memory for your strings at some point, but you usually don't count this up in advance, right? You usually don't sit there and know, okay, I can only have 5 billion strings, I better make them count. And that's the way you should think about virtual threads. Just use them when you need them. And if you should indeed run into limitation because of that, then it's the time to look into that, whether you need to fix it, just like with the strings. The cool thing about this is that you can create new concurrency programming models. Strictly speaking, specifically talking about structured concurrency here, but first, structured programming. So who here has programmed, who here knows what structured programming is, the term, who understands the term structured programming? Really? Who studied computer science? Okay, I got bad news for you guys, because you definitely learned this in computer science. So before we had functions and methods, we had gotos. And then at some point, some guy named Dijkstra figured out that, maybe just having gotos everywhere is not a good idea. Maybe we should have like dedicated entry points and dedicated exit points to the logic that we write. And born was the idea of structured programming. And this is so ingrained in our everyday programming, you can't even program any different way. Like you could argue that Java exceptions are kind of like a specific version of goto, but otherwise you just have to have the single entry point into every method, and then you can have multiple exits though. Okay, so that's structured programming. So I tried to say, okay, instead of allowing you to do everything because that leads to unmaintainable code, let's put structure in that appears limiting, but actually frees us because we now understand the code better. And structured concurrency wants to do the same. When the flow of execution splits into multiple concurrent flows, they rejoin in the same code block. That's all this says. So you have one method, and if you say, I want to fan out 5 tasks here, then structured concurrency says, within this method, you're going to capture all the remaining tasks and the results, and then you're going to keep going. So these threads are very short-lived, and the thread that is waiting for these other ones to finish is kind of like their parent, right? There's a parent-child relationship now because these threads do have a limited lifetime that only exists basically while the parent thread is waiting. And this parent-child relationship allows interesting things to do. So this is what a structured concurrency API would look like. That's the current proposal, which is at the moment only available in the Loom early access builds. So this is not yet available in JDK codebase, in the main line, but it will probably be available in a couple of weeks or months. Okay, so what we're doing is here, we're saying we're creating a new structured task scope. We'll open that up. It has some behavior when it comes to short circuiting. We're going to talk about that in a second. You fork these subtasks. I'm forking subtask A and B, so I get something back, which is kind of like, you can think of it a little bit like a future. You're getting a promise back that you will later have a result. Then you wait. That's what join does. We're going to wait. And in the end, you can call subtask A get and subtask B get to get the results out. And this looks fairly straightforward, and it is. What this does, though, is because these two forked tasks are specifically created in the structured task scope, as I said, we have this parent-child relationship, and that can be used, for example, to handle how errors are propagated. So if task A fails, this specific structured task scope I'm using here will say, well, we want all things to succeed. If one of them fails, I'm immediately going to cancel the other one, which in Java terms means I'm going to interrupt that thread. Join is immediately going to return, and then it's going to throw an exception, and then down here I have to do exception handling. And then we never got to the response.send. So this task scope knows I fork 2 things, and I want both of them to succeed. But that's not the only behavior you can have. You can create a joiner that deals with details. So for example, how are results collected? Do you want all results or just one result? Do you care about failures, or do you just let those play out? When are subtasks canceled? That plays into that. And under what circumstances does join throw? So that's all tasks of the joiner, and then you can pass the joiner to this structured task scope open. And there exist a bunch of joiners that are already implemented. So these 2, for example. Await all successful or throw, which means what I basically just said, I want all of these subtasks to be successful, and if one of them fails, I immediately cancel everything and throw an exception. That's the default behavior. But there's also an await all, which never cancels or throws. So, always all tasks will wait for completion, and then you have to figure out, oh, the first one failed, but the second one succeeded. I'm happy with that. Maybe that's the one you need for your logic. If you have homogeneous results, meaning maybe you have 5 threads that all create an instance of user, you can use a joiner for that, and that makes the API even simpler to use, even though I'm not showing you how, but you can read the JEP and you'll see. All successful or throw is like the first one before, which is it throws on the first error, but now you get back a stream of these results. So you can be sure that you called these 5 subtasks and back comes a stream of results, Or maybe you don't care about all 5. Maybe you just care about the first one. So then you do any successful result or throw, and if one of them succeeds, then you get a result back. So there's already some kind of behaviors implemented here, and you can create more and plug that into a joiner and give that to a structured task scope. And if you want different behavior here, so maybe you want to fork with a timeout here, or want to do some other fancy stuff, there's nothing magic about this structure. It's just a try with resources block. So you can create your own structured task scope that wraps an existing one, that wraps one from the JDK, and adds a little bit of extra behavior as you see fit. Just make sure that your close forwards to the other close call, and then you're all good to go. Another thing that the structured task scope does is it embeds information in these virtual threads. Let me go back to, here. It creates this parent-child relationship. And this is so far only visible in thread dumps, unfortunately, but it's already really cool there, and I hope that will be made available through IDEs at some point, where when you make a thread dump and you see like, okay, so there's a problem in this thread, and you go up the threads, you know, the call stack, you sometimes, or in a highly concurrent application, usually end up in the root of some thread pool that called this function, that called this method on the thread, and then you're lost. You don't know the context. You don't know where else to look. But this is not the case here, because every thread is just a child of some other thread. So that thread actually knows what the parent thread is. It has an owner ID which points to the other thread's ID. So if it's virtual threads all the way down, and once this is available in the IDE, you can set a breakpoint wherever you want. You can navigate to the top of the call stack, and if you're unhappy, you can jump to the parent thread. You can see, oh, this one is waiting in join. So what was the state here? What did it pass on? Maybe I walk up that call stack. And if it's virtual threads all the way down, for example, Helidon has working with virtual threads, starting from reading the WebSocket that gives that where the bytes come in, you can go all the way up to where the request was first entering your application. So that really will unlock much more insightful debugging. That's really enthusiastic about that, because that's like, imagine you could not debug with a navigable call stack. And I'm pretty sure in 5 to 10 years we'll think the same, like, how did we debug without being able to navigate from one thread to the parent thread and just see what its state was? And also the structured concurrency API does give you success and failure policies that can be defined across all these children. Okay, let's talk about sharing data a little bit with thread locals. Do you have questions about structured concurrency? No? Good. Not good on time, by the way. I'm doing kind of terrible, to be honest. Okay, let's talk about how sharing data with thread locals. So this is the API. If you ever use thread local, you know this. If you haven't, it's not terribly important. What you're doing here is you're setting data, you're making data available in a way that every thread has a different view, so that you don't share instances across threads. And this API has some downsides. The fact is that everybody can just set, everywhere in the thread, you can just set a new value, so it's very mutable, right? Like that you can never rely on what's there. The lifetime is unbounded. When you have put stuff into thread locals, you are running the risk that you have a memory leak and that you will not find that data will later still be around. And inheritance is kind of expensive. You can inherit a thread local from one thread to the other, and then there has to be a full copy. And so that makes it expensive. Now think about virtual threads, where you maybe have hundreds of thousands, maybe even millions of virtual threads. These copies can eat up memory quickly. So they work correctly. Again, these things work correctly with virtual threads, but you don't get the scalability you want. Scope values improved on that. They improve on the programming model with the write once per thread program model. It's clearly scoped, and at the end of the scope, the data is definitely going to be removed again. And inheritance is free, because when it's immutable, you don't need to copy. Right? There's no reason to copy or make a copy of that thing. It looks very similar, but you can see the scoping here. We're saying, okay, scope value where this principal has this specific value, we're saying the specific value here, and there where this value is set, there we run this method. And so that means in that thread, that value is readable, and once that thread completed, the data will be removed again. So Project Loom does all of this, right? It's about concurrency in general, and specifically it starts with virtual threads, which make code easy to write and debug and profile, while having high throughput without this trade-off, right? So simplicity and scalability. And then on top of that, build structured concurrency with the cleaner code and simpler failure and success policies with this better debugging capability that I mentioned. And then scope values improve on thread locals program model, if immutability is okay for you, that's definitely the requirement there. But it also makes data sharing more scalable with many virtual threads. If you're on JDK 21, you can use virtual threads in production. They did finalize, they're all good to go. Structure concurrency and scope values API were still in preview. Now, 3 releases later, still in preview. But we learned that on JDK 24, the pinning of virtual threads when you interact with object monitor are gone. So there, 24 definitely is a leg up. The scope values API changed, I think, not at all, or if they did, just minor. Structure concurrency changed a little bit. But let's start at the bottom. Structure concurrency will change again. It will definitely get another preview, and it will change. So don't write code against that you're not willing to rewrite. That's always true for preview features. As I said, they are stable in the sense that they don't crash your VM. They're not alpha or beta versions, but they might change, right? And we know about this specific preview that it will definitely change. Scope values, I don't know. Maybe they will finalize in 25. Maybe they won't. Other work besides these 2 APIs is improve the log information in thread dumps so you can better see which logs are being held. And then the pinning during class initialization is something we skipped earlier. It's a minor pinning issue, but it's also something that seems resolvable. So there's work in that area to see whether that can be removed. Lots of links to go deeper. Let's keep going. Yes?
Earlier today we saw a presentation that spoke about continuations.
Yes.
Are there any plans for making that non-internal?
So the question is, do we have any plans to make the continuations which underpin virtual threads a public API? No. I don't know what the considerations there are. I know that the answer is no, but if you want to know more details, you can probably check the mailing list, and if nobody asked this question yet, go ahead and ask it. And if nobody answers, ping me. I'm gonna ask. I'm just like, Ron, give an answer. So I always think it's good to have these kind of reasons publicly available, so that that we know why, at least, why that's the case. Another question back there. Yes. But so what you're asking is, like, if virtual threads and thread locals don't quite harmonize, should there be like a warning or some signal, right? Yeah. So since thread locals and virtual threads do work correctly together, and the scalability issue only becomes an issue in certain circumstances where you are trying to scale those virtual threads across those thread locals specifically, I think that's too weak. I think there are many other ways that you can use Java in a way that doesn't, for example, you catch an interrupted exception and you just don't care, you eat the interrupt and you just keep going, right? That's not good. That's a problem if you do that. But you can write that code. No JVM is warning you about that. So I think the situation that you're describing does not rise to the level where it really makes sense to keep track of that and then explicitly warn the user, because it's not like unsafe. Like, unsafe really is unsafe because it might just go away in a future release, or it will go away in a future release, in fact. So I don't think that that's something that is being done. I'm quite sure that it's not. I'm wondering whether you could do something like that yourself. If you attach like an agent or something that could do some smart things there. Yeah, but the library providers, they could switch to scope values if their code allows that, right, on a new Java release. Let's cut this short. Let's talk about this later. I think we'll make it like a 2-person conversation. Then I can more easily follow you as well, because I don't hear you that well, okay? Let's talk after. Good. Good. Let's see what we can speed through. I'm a little bit disappointed in myself about the timing here. Maybe I can get a couple minutes. Maybe we can go a little bit into the break, because I think you have like 15 minutes before your talk starts. Is that correct? No? So we'll see. Maybe just somebody has to drag me off stage. Let's go a little bit into Project Leyden. It's about faster startup, shorter time to peak performance, and smaller footprint. The motivation here is that Java does have great peak performance, but the startup and the warm-up time is slow. So what's startup? Startup is you start the JVM, and then the first statement in your main method gets executed. That's startup. And warm-up is from there all the way to peak performance. That's startup and warm-up. And those tend to take a while. A while means lots of seconds, probably not minutes, although that might also be the case, depending on the application. But we're not talking about hours here, right? But still, you know, ideally you want things to be just snappy and work immediately. And a large footprint, that's also something Java has compared to more native languages. And Leyden for now focuses on the first two. So what is happening during that time? There's two kinds of computation that are executed at all in the JVM. The most obvious one are the computation that you express in your program, right? You write a statement, so clearly you want that statement to be executed. That's work that needs to be done. But there's a lot of work that is being done on your behalf. Class loading, JIT compilation, the garbage collector. They all do work so that your program can do its work. And again, for now, Leyden focuses on the latter and asks, how can we get some of that work out of the way of startup and warm-up? And there's a lot happening there in the beginning. Class loading, call side linkage, class per resolution. I'm not going to talk through all of this. In the end, you have JIT compilation, which is really the thing that kicks from startup into warm-up. That's what takes so long, right? To observe the application running for a couple seconds, to find the hotspots, hence the name of the JVM, and then optimize with just-in-time compiler. So that's a lot of things that happen during startup and warm-up. Java already has a concept of shifting computation around, of doing things at a different time that you might expect. So for example, if you ever had a public static final int foo equals 0, and you used foo elsewhere, you might have noticed that that code, that bytecode that gets compiled, doesn't reference foo anymore. It just straight up uses a 0. That's called compile time constant folding. Class loading is as lazy as possible. You could imagine a JVM that starts and just reads all the jars, but it doesn't. It reads only exactly the classes that you need, and it does it as late as possible. Garbage collection means we don't clean up now. We'll clean up later when delete memory. So we're shifting again to the back end. We're making it as late as possible. And then you have out-of-order execution. The just-in-time compiler will just take your statements and shuffle them around, making them earlier or later, depending on what it thinks works better. And the idea here is, let's shift more computation ahead of time. Let's move computation that happens during startup and warm-up and move it into a different phase that happens before you launch your application. Now, what computation do we want to do ahead of time? Ideally, just all the things. Ideally, everything that the JVM does would be done before, and then it just immediately starts executing your code. But, I mean, there's a lot happening, again, and if we look at that, we notice that a bunch of that, like that code elimination, for example, can't really be done before because we don't know all the details. The reason why Java is so dynamic, the reason why Java does it as launch time is because only then does it know all the circumstances, only then does it know the CPU architecture, what dependencies you have lying around, how many implementations of interface it has, and where to dispatch methods. Only after running for a while can it find out what methods to optimize and how. So there's a lot that is inherently dynamic that how do you do that before the application actually starts? And the ideal case here would be a crystal ball. So that's what we ideally want, right? We ideally want to do everything ahead of time because our crystal ball tells us what to do. Now we don't have a crystal ball. Next best thing is a training run. The next best thing is let's run the application and then let's see what it does and then let's capture all of that information. And a training run could be integration tests, performance tests, could be a canary deployment that just runs in production for a couple of minutes, and then you take the information from there, and then you use that information to create this AOT thing I'm going to talk about in a second, and scale up. So Project Leyden introduces the so-called AOT cache. And the idea here is observe the JVM, capture all the decisions in the AOT cache, which is an expansion of the CDS archive. If you've heard that term before, CDS archive is now evolving. It's now the AOT cache. The idea is stuff more information in there. And then we use that as an initial state during a future run. But importantly, it realizes when things don't line up, it can still de-optimize. It can still notice that dependencies are different, and then it falls back onto the original behavior. You pay a price. You don't get any of the performance benefits, and you might actually pay for it having to go back and redo decisions. But it will behave correctly. That's important here. And this is how you could do this. Already in JDK 24, you can do this. You run the application, once up here with like, okay, record please and create this configuration. Then you don't run the application. You just run the Java launcher and you give it, you say, create an AOT cache, please. Here's the configuration. Create this AOT file. Here's the class path. Now do your thing. This is not application execution. This is just Java using the profile information to create the AOT cache. And then later you run the application and give the AOT cache. This three-step process will probably be improved and streamlined in the future. There are lots of details that could be done here. But overall, that's like the steps you should have in mind. Okay, now specifically, this is the first thing that landed. JEP 483, which is part of JDK 24, says we improve startup time by making the classes of an application instantly available in a loaded and linked state when the hotspot JVM starts. So this is AOT class loading and linking, which were two of the many bullets I listed earlier. And benchmarks show an up to 40% improvement. Of course, that doesn't mean that you all get 40%, depends on the application a lot, so do try out yourself if you care about that. In this specific Spring Pet Clinic example, which includes all of Spring, the AOT cache was about 130 megabytes, just to give you an idea. So we are not talking about like 5 megabytes here, but it's also not in the gigabytes, depending on the application. If it's a big Java backend, it's probably larger. If it's a microservices, it might be a little bit smaller. Also depends on what framework you probably use. So yeah. Now, as I said, we want to AOT everything. So there is a Leyden early access build, which does ahead of time work on a lot of more of these things. And that at the moment shows like a 70% startup improvement on the benchmark on this application. But again, this is not something to bet your house on, and this is very early. It just shows that there's still much potential in doing all of that other stuff and pulling mode as much as possible ahead of time. Yes? Yeah, let's talk about Java on crack at the end towards it, yes. Right, so the question is how that's handled. So there are limitations here, which I come to in a second actually. I'm going to go over that list, and then I think that might be at least partially answered. And so most of this data can be validated at runtime, and it can be replaced with more accurate or better data, for example, JIT data at runtime. So if it turns out that your training run is not ideal and actually overemphasizes some parts of the code base that's not the main path that is run during execution, or more importantly, if some branch prediction is wrong, it will de-optimize and does its usual thing, so it will be correct later. But more optimizations are possible if we just constrain Java's dynamism. And if the program is constrained as well, if you are willing to accept limitations on your program, there might be even more possible. So for example, some constraints could be you cannot redefine every class. Only certain classes can be redefined, and then all the other classes can see better performance improvements. Then something that Graal does is a closed word assumption. We assume that at this time we know everything that's ever going to happen. That gives the system the most leeway to do optimizations. But maybe you say, look, my configuration YAML file, I defined that during build. I never change it again. So why not read the file, do all of that, and then dump that state? So you can accept even constraints not on what the JVM does, but what on your program does, and then get further optimizations. And the idea here is you think through what of these constraints am I willing to accept? And then the JVM just looks at that and says, okay, this is what I can do for you. So I'm then doing the most that's possible. Okay, I'm actually kind of wondering, where's my new slide? It should be somewhere here. I made a new one. We're going to come to the limitations though. Okay, I'm going to get there in a second. Let's summarize this, let's do the timeline, then I'm going to answer both of your questions. So the idea is that Leyden improves Java's overall startup and warm-up footprint, which is what it is focusing on for now, by caching all the work that JVM is doing in the beginning. But in the future, the goal is, this is probably going to be a long-running project, which as it picks the low-hanging fruits, we're going to get high up the tree, come up with more constraints, and then give you more power, or not maybe necessarily more powerful, but just give you additional optimizations on top of that. So that's the goal there. In JDK 24, you can already use AOT class loading and linking. That's a final feature there. And then there's work on code compilation, AOT code compilation and method profiling. JEP drafts exist for both. And as I said, work towards more limiting constraints is also underway. There's more links here, and I'm still weirded out by my slides missing. Okay, so what are current limitations? This only works if you run the same JVM on the same operating system with the same CPU architecture. Your class paths should be the same or the production class path, like the training class path can be a prefix of the construction class path, but otherwise that needs to be the same. And then JVMTI agents who can do all kinds of stuff are limited. Like if they should not do all kinds of stuff. There's limits to what they are allowed to do so that these optimizations still work. And as it comes to the order of these initializations, I talked to Brian about this earlier. He said this is going to be a problem, but at the moment it's not, because with class loading and linking does not include running initializers. Class initializers, which is executed code, which might depend on order, that's a problem down the road. But I can give you a preview. Most classes don't have an initializer, so those are all good. There's a very limited amount of operations that the compiler could prove that these are safe. You probably get improvements for that as well. And after that, it gets murky. It's probably manual intervention where you have to say, look, this one is fine, this one isn't. Okay, and how does it compare to Crack? So one issue with Crack is that because it snapshots the entire VM, that means open file handles, system current time millis, whatever measurements you took, whatever things you have open, those are just all frozen and then revived, and you have no realistic insight into whether they are still up to date or not. You have to depend on you or all of your dependencies implementing these hooks correctly, which at the moment is just not the case for many dependencies. And one way that Brian gets put it is, it requires you to debug your way into safety, to debug your way from an inherently, if not buggy, then at least system that you're not sure whether it does everything. And then you have to keep running it and see, oh yeah, it looks like all the file handles are working. Until in production you find out, nope, there's this one thing that we still didn't catch, and we get another crash. And the Java has always been very adamant on not doing it that way, but starting at the safe end, giving you everything that works, guaranteeing that everything works, and then try to see how far can we get with these guarantees, and then maybe tell you explicitly, this is how you give some guarantees up if you are willing to do that. Instead of saying, it's probably working, but we're not sure, you have to find out, please do some debugging. So that's why I think that Crack is probably not going to get very far within OpenJDK. Yeah. And now this is, I'm ashamed to say, half of what I want to tell you. It's not quite half. These other projects are faster. I'll give you a quick rundown. Project Valhalla, value types. Everybody knows we want to have value types. When will we have value types? Nobody knows. But JEP 401 is the tip of the spear, and Brian Gertz is really working hard together with the rest of the team to make that a thing. I don't want to say it's going to happen this year, because I said this for the last 3 years. Literally, I said this year, not 2025. So I don't want to make that. I don't want to utter that hope anymore, because I do hope it's going to come soon. But there are early access builds you can experiment with, and I hope that JEP 401 will land soon. But that's just, as I said, tip of the spear. That's just about value types. There's so much more coming behind, and Valhalla will keep us interested and busy for quite a while. Babylon is about giving libraries that are not part of the JDK the chance to take Java code and run it on a GPU, or as a database query, or as a mathematical function that gets differentiated in part of a machine learning system. The idea so is here that you write Java code, and reflection API will not stop at a method. At the moment, a reflection API cannot look into a method, but that you will have a way to say, no, this method, I really care about the internals, so that the internals of the method, the statements, become available kind of like an abstract syntax tree, but not the AST from the compiler, also not bytecode, something in between that will become available to these libraries, and they can then transform that and push that onto the GPU, for example. And there's one specific project that is being worked on as well as part of Project Babylon, which is the Heterogeneous Accelerator Toolkit, HAT. And HAT is doing that. HAT is using those, and then is using this API that is under development, which is called code reflection and code models, to push that onto the GPU. But it's important to understand that this is not Java saying, this is how you write Java code for the GPU. The main thrust here is to say, we want to provide other libraries with a chance to find out the best way to do this, so that we unlock the creativity and the work in the ecosystem. And there will be one implementation that does this on the Java side, probably, or one is at least explored right now. But the main goal here is that everybody can interact with that. I mean, not everybody. I probably won't, because it's pretty complicated, like code models and having to but put instructions into like CUDA-C. Not my thing, but those people who can do that they can then interact with it. And then Amber Amber has been the powerhouse of Java's language evolution for such a long time. This has been all the delivered features in Amber. There's a bunch of things that are still being worked on in Amber. Amber is not a project that has a clear endpoint. All the other ones have a goal, and once that goal is reached, like Jigsaw, which introduced modules, the project kind of like dies down. It's not closed, you know, the mailing list still exists and occasionally something happens, but it's not like seeing a lot of resources worked on because, you know, the goal is achieved. Whereas Amber is in a situation where it will find things to improve in the language. We'll basically do kind of like an optimization, right? You remove one bottleneck, you see where's the next bottleneck, what's the next thing we can improve, and then it will go there. And there are so many ideas in the line. These are just the ones that I know that are publicly available. I'm pretty sure that Brian in his famous notebooks has tons more ideas that didn't share yet. So a lot of that is going on as well. Okay, so if you want to learn more, I'm NipaFX on all the platforms. Importantly, on inside.java, that's the page to follow these projects along. That's where we collate all the important JEP publications, all the good emails from the mailing list, videos we make on those topics. Everything goes to inside.java, has an RSS feed for the old people among us, like me, who enjoy those kind of things. So you can follow along easily. Usually it's like 3 to 5 posts a week maybe, where you can track how OpenJDK is moving as it happens. And otherwise, the Java YouTube channel, where you can hear more about me, from me, I mean, not about me, from me about Java. And with that, I want to say sorry once again that I didn't get into the level of detail I wanted to in these other projects, but thank you very much for your attention and sticking with it. So let's do the switch over now, and I'll just go to the back of the room if any...